Okay, so it's the last lesson in Unit 3. We're going to discuss how other ways to find enthalpy. Okay, remember that enthalpy is heat energy. All right, and we have several ways to calculate it. One is what we've already focused on. That's using calorimetry, experimental information, where we find Q and then use mathematics to convert it to an enthalpy value. The other three that we're going to look at today include Hess's law, where we're going to combine some things to find total enthalpy. We'll use the delta H of formation, specialized thing to find our reactions, and we'll also be looking at some bond energies, okay, and how we calculate enthalpy from those. So let's recall, just for a minute, that enthalpy is affected by basically three kinds of things. So let me make this screen a little different. Okay. So enthalpy is affected by the amount of material. So we've seen before that if we know something about how much heat is released if we use a certain amount, like 10 grams, then we expect if we use 20 grams that we'll have about 2 times that amount of heat. We've also looked at changing the reaction in a different direction and how that causes us to need to change the signs, okay? Because in this direction, we're going from A to B, we get minus 100 kilojoules. Or if we go from B to A, well, then we would expect 100 kilojoules of positive heat. Finally, there are additive reactions, okay? So maybe we don't know enough about any particular thing from A to C, but we know about A to B and B to C, and so we can use that information to figure out a difficult reaction to do. What? All right, so just to summarize, okay, just a review, if you reverse the reaction, you just change the sign of delta H. If you have different coefficients from what you had in the balanced reactions, then anything you do to the balanced reaction, you would do the same kind of operation to the delta H of enthalpy value. And then if you have something more than one equation, you can manipulate those equations, remembering that anything you do to the equation, you have to also do to the delta H, and then you can add them up. Now we'll start with Hess's law. So why is Hess's law something people use, or something that we can use, where we just add up a series of different reactions? That's because recall that enthalpy is a state function. Okay, and what that means is it doesn't matter where you start or how you got there. It doesn't matter where you start. The only thing that matters is where you start and how you get there at the end, not what pathway you use. So any enthalpy, we'll just say total, is going to be the enthalpy for one plus the enthalpy for the second one plus however many more delta H of enthalpies there are, okay? Because it's a state reaction. It doesn't matter if you start at 12 and go to 14 and then 3 and then the 5. Only thing that matters totally in the end is the total, okay? So we can just add things together to make them work out like we want to. So let's look at our first example. Okay, this is a Hess's law example, and in this case, you need to identify what you know. Okay, this is your target equation, basically. Your target reaction, it looks like that, and you're going to use these two reactions. Okay, you're given a couple of 3 reactions, and you're going to manipulate them to make them look exactly like this target equation. So in this case, we want to get some 3 hydrogens and an ozone to form 3 water molecules, and we know about hydrogen and oxygen forming water, and we know something about oxygen forming ozone. We can put these together to make a decision. So basically, you just have to rewrite equations until you get everything done. You can't be lazy about this. Okay, so first of all, I'm going to make sure that I'm going in the right direction. If I start with the hydrogen, in this case, I have the reactants on the same side, so I'm happy about that, and I end up with the same product. However, I don't have the same coefficients. Okay, so I'm going to have to do something to get them to get this reaction to have the same coefficient as my target reaction. So I could just take 3 halves times 2H2 plus O2 yields 2 H2Os. Okay, and if I do that, that also means I have to take 3 halves of my delta H, which is negative 483.6. Okay, so when I cancel, this is going to give me the same coefficients as I had before. I'm not going to put this together for just a minute. I just want you to see that by multiplying by 3 halves, I'm going to end up with the right value, the right number of, for the coefficients. Now, and just, I want to focus on this reaction and this reaction for a minute. But first thing I see is that I have an O3 here as a product, but an O3 here as a reactant. So I need to turn this equation. All right, so that means I need to change this to 2 O3s forms 3 O2s. And what am I going to do with this delta H? I'm going to change this sign. Okay, it's still the same reaction, it's just going in the opposite direction. So I expect the same amount of heat. So I just changed the sign. But I'm not quite done because I can see that I have only 1 ozone there and 2 down here. So I'm going to divide everything here by 1/2 as well, which also means I'll divide everything in the enthalpy value by 1/2. So let's look at putting this together now. So you see I've had to write 1 set so I could just sort of get started. Now I want to clean that up and make sure that what I get in the end is going to total up to my target reaction here. So I'm going to end up with 3 H2s plus 3 halves O2 forming 3 H2Os. And that delta H is going to be equal to negative 725.4 kilojoules. So there I've handled the first given equation. And then I'm going to I'm going to do the same thing and clean this up some. And so now I have O3 yields 3 halves O2. And for my delta H reaction here, this is going to be negative 142.3. Now I'm going to extend this page, so please remember that this is what we're going to get targeted to. But I've run out of space here, so, oh good, we still can't see it. So now I'm going to add everything up. All right, so the 3 halves oxygen is going to drop out. I have 1 on the reactant side and 1 on the product side, so that will drop out. And then if I add everything up, I'll get 3 H2s plus an O3 forming 3 H2Os, which was what we were looking for in our target equation. And therefore, when I add up all of this delta H that I calculated over here, I'm going to find my delta H is negative 867.7 kilojoules. Okay, so when you do Hess's law, you find the target equation, and then you manipulate the given equations. Anything you do to the given equations, you want to do likewise to your delta H, and then you Set it up so you can clean it up, and then make sure that what your target, what you've got down here, is the same thing as what you're looking for. Okay. And whatever, if that's true, then you just add up your delta H's. All right, so that's Hess's law. Now I want to move into thinking about something called the heat of formation. Okay, so we're going to find our delta H. I just make reactions so it's clear, given some values that have been tabulated and found in a table in the back of your book called the delta H of formation. Okay, so the heat of formation, this is the standard heat of formation. That's what that little knot means. It means standard. And everything in that table is the standard heat of formation. And it's the enthalpy that's associated with the formation, and this is important, of 1 mole. Okay, 1 mole of some compound from its elements, only its elements, when they're all in their standard states. Okay, in their standard states. So, what are elements in their standard states? Those would be the atoms in the periodic table. For example, carbon, which, by the way, in its standard state is a graphite. Aluminum, in its standard state, is a solid. Neon, in its standard state, is a gas. What else might you need to be on the lookout for? Well, you remember those 7 elemental molecules. H2, N2, O2, F2, Cl2, Br2, and I2. All of those are elemental molecules, and these are all gases. Okay, that's its standard state as a gas. This one, bromine, remember, is standard state of a liquid, and iodine is standard state is a solid. Okay, so you should be kind of watching for those. Anyway, we can use these delta H of formations that are in this table to find whatever our reaction is. So let's talk about standard state for just a minute. Okay, the standard state is 1 atmosphere for gases and 1 molar for aqueous solutions. I know we haven't, well, we have talked about molarity a little bit in Unit 2 when we determined how to make a solution. Okay, so that's the concentration, and so is an atmosphere. Of course, we need pure substances. Okay, so we just want iron if we're talking about iron, and we want iron, or whatever the substance is, in its most stable state. Okay, so iron in its most stable state is going to be a solid. So, in your table, you need to be careful in the delta H of formation table because some of them have more than 1 physical state. Okay, so you need to be watching for example, iodine as a solid and iodine as a gas. All right, so this has nothing to do with calculating the enthalpy right now. I want you to be able to write a formation reaction though. Okay, so a formation reaction, recall, is forming 1 mole of some compound from its elements. So we got sodium bicarbonate here, okay, and so we need to take this apart and look at it and decide what the elements are for starters. Well, sodium is an element as a solid, okay. Hydrogen, that's not just a hydrogen atom. The element in its standard state is H2, okay, and we've got a carbon, which in its standard state is a graphite. And we have some oxygen. And remember, oxygen has to be an O2 molecule. So, we have to now remember that we want to form 1 mole, just 1 mole of NaHCO3. And so you'll have to manipulate these things to give you just 1 mole. So sodium, I have 1 sodium on both sides, that's good. I have a hydrogen on this side, but an H2 on that side. So I'll need to make this 1/2 of an H2. We should consider this 1/2 of a mole because you can't have just a half of a hydrogen molecule. We've got an atom of carbon, and then we're going to have 3 oxygen atoms down here. So we'll call this 3/2 of the oxygen gas. And that would be a formation reaction where you make 1 mole. Now this goes against what we learned when we were balancing reactions, where we couldn't have a half of a hydrogen molecule or 3/2 of an oxygen molecule because we're only trying to make 1 mole. So these are all considered moles, not molecules. Okay. What about glucose, our favorite? Glucose. So I want to find everything from its elements in their standard state. So I'll have 6 carbons as graphite. The other option in the table is the diamond, and that's not in its standard state. Plus, now I've got 12 hydrogens here. So to make 12 hydrogens, I need 6 H2s. And I have 6 oxygens, so I need 3 O2s. And that will form C6H12O6. Okay, so you should be able to write formation reactions. You should be able to figure out what those values are, what those elements are that will make up 1 mole of whatever you're looking for. All right, so now that's what the delta H of formation tables are. They're how much energy it takes to form 1 mole from its standard state elements. All right, so now that we kind of know where those numbers come from, we need to find the reaction. We want to know how much we have for some given reaction, for that enthalpy value. We'll take the sum of the number of moles with each delta H minus the sum of the number of moles for each delta H. Remember, this is products minus reactants. It always has to be set up like that or your signs are going to be wrong. So be sure to subtract the reactants from the products. You'll need to multiply delta H of formation by however many moles there are in the balanced equation. And you also really got to pay attention to your positive and negative signs. All right, so I wish you'd look in your book for a minute at the back of the book, and you'll see a table, okay, and in the table, thermodynamics table, you'll see a delta H, a delta G, and a delta S back there. Oh, I'm sorry, it's just an S technically. Okay. For our purposes, we don't care about that. That's in thermodynamics, which we're going to study in Chem 2 in this class. But at any rate, what we care about are these delta H values. They're the first ones. Be sure you pick out the delta H of formation, not one of these other options in the table. Okay, so now we've got this reaction where we're going to take, and I wish I could make you say this, but I'll say it, dinitrogen pentoxide, 2 of them, and form some nitrogen dioxide and some oxygen gas. And we're going to figure out how much heat would be released from this. So following our formula, the delta H of formation is equal to the sum of the delta H formation for the products minus the sum of the delta H of formation for the reactants. Okay, so that's what we're going to be looking at. So, what do I know? Starting with the products, which is where I need to be. Sorry about that. Starting with the products, which is what I'm interested in, I'm going to notice that I have 4 moles of nitrogen dioxide, and I'm going to look up in the table, and I'm going to and also that's in the form of a gas. I'm going to look up in the table, and I'm going to see that it has a value of 33.2 kilojoules per mole. Then I'm going to look in the table, and I'm going to see that for a mole of oxygen, the value is 0 kilojoules per mole. Okay, so I'm going to sum all this up. It should be pretty easy. And then I'm going to subtract. Okay, be sure to subtract. This helps keep your sign right. The products. The reactants here. And when you look in the table, you'll see there's a dinitrogen pentoxide for a solid and a dinitrogen pentoxide value for a gas. In this particular case, we're interested in the solid. And so in this case, we'll take 2 moles of nitrogen pentoxide times its value in the book, which is negative 43.1 kilojoules per mole. Okay, and if I had more reactants, I'd add those in, but there's just one here. So, taking these values, I'm going to see for my products, I get a value of 132.8, and from this, I'm going to subtract negative 86.2 kilojoules. This is kilojoules as well. So this ends up being 132.8 plus 86.2 kilojoules. And so in this case, this is an endothermic reaction with a positive 219 kilojoules of enthalpy for the reaction. Okay, so I want to point out a couple of things. You've got to remember to subtract. You've got to be watching these signs, okay, because they make a big difference. In this case, we ended up adding, right? So if you get it turned the wrong way, you're going to get the wrong value. All right, so be very careful with that. Here's an example from about iodine. Okay, we're going from iodine gas to an iodine solid. And so in this case, when we write up our delta H of reaction, this will be 1 mole of I2 times the delta H of reaction for the solid, which in this case is 0. I should talk about that some more in just a second. And then I'm going to subtract 1 mole of I2 in its gaseous form, and that value is 62.4. Yep, 62.4 kilojoules. And so the delta H for this reaction is negative 62.4 kilojoules, an exothermic reaction. You see, you never have to worry about what the sign about whether you need to change anything in this. When you come up with a negative number, assuming you've done your reaction calculation properly, you know that that's exothermic, or you know that this is endothermic, because the sign says so. Now, one thing I didn't talk about, but I should have, is the delta H of formation for standard state elements. Standard state elements is always equal to 0 kilojoules per mole. Okay, so oxygen O2 is 0 kilojoules per mole. Carbon as a graphite is 0 kilojoules per mole. Neon 0 kilojoules as a gas is 0 kilojoules per mole. So anything in its standard state in the enthalpy value, in the enthalpy table, is going to be a 0. All right, one more thing I expect you to be able to do, okay, for our enthalpy is I still expect you to be able to do a combustion reaction. Okay, so we're going to combust this, and I expect you to still be able to do this. What are the rules for combustion? Every carbon forms a CO2. Hydrogen, not every hydrogen, but hydrogen forms H2O. We're gonna, for our purposes, unless I say differently, we're gonna assume that those are gases. And let me say it this way. Find the coefficient of the O2 after you balance your equation for everything else. After that. So, we're going to take butane, C4H10, and we're going to do a combustion with it. So I'm going to take C4H10 plus some oxygen. I don't know how much yet, so I'm going to leave that alone. Then I have 4 carbons. So that means I'll make 4 CO2s, gases. And I have 10 hydrogens. Now I'm going to form water, H2O. So I'm going to form 5 H2O gas molecules. Then I'm going to add up on this side, and I'm going to say, okay, I have 8 oxygen atoms here, and 5 more over there. So I have 13 oxygen atoms on the product side. So I'm going to come back on this side, and I have a little difficulty here, right? I have an O2, but I have an odd number of oxygen atoms. So to make that be 13, I'll take 13 halves. Now remember, that is not legal in balanced equations. We can't have a half of an oxygen atom. Okay, so that means we have to multiply everything in here by 2. So our final reaction will be 2 C4H10s plus 13 O2s. And this is gas, and that's gas, forming 8 CO2 gases and 10 H2O gases. And that's going to be your combustion reaction. This is a gas, that's a gas. Okay. Now, how's that different from the formation reaction? That's a specialized balanced equation. Okay. This one is what you're supposed to be doing when you balance equations, except for the formation reactions. So I expect you to be able to find the combustion reaction, because you're going to need this in order to find your delta H of reaction. All right, so given our final balanced equation here, okay, I'm going to determine the delta H of the reaction. So in this case, the delta H of the reaction is going to be 8 moles of CO2. You'll look up the value for the gaseous CO2, and that's negative 393.5 kilojoules per mole. Plus, remember, this is a sum of all of the products. 10 moles of H2O in the gaseous form, and you look up that value, and that's negative 241.83 kilojoules per mole. So I've taken care of the product side of my balanced equation. Now, I'm going to subtract from this product amount my reactants. And in this case, this will be 2 moles of the butane, C4H10, times the delta H of formation for that, which is negative 126 kilojoules per mole, plus 13 moles of O2. And what's the value for that? 0, because that's in its standard state. Okay, and I'm going to sum up all of this stuff. So for the first part, when you sum up, you get, well, I'm going to sum up this way, negative 3148 kilojoules for the carbon dioxide. Then I'm adding a negative, so basically for the water, minus 2418 kilojoules for the water. Those are my reactants, my products. And then I'm going to subtract out the reactants, which turns out to be minus negative 252 kilojoules. So, negative 5566 kilojoules for the products, plus 252 kilojoules for the reactants. And so my delta H of reaction works out to be negative 5314 kilojoules. Okay, so you've got to be watching the signs. You've got to set it up right, products minus reactants, and you need to be very careful that you actually pick the right thing out of the delta H of formation tables, depending on the state of whatever you're working with. Okay, so that's just a short kind of enthalpy using the delta H of formation, something that people have tabulated and you have access to in your book. Now I want to look at the last way that we can calculate the delta H of the reaction, and we can do that using something called bond energies. Okay, so I want to talk a little bit about bond energies before we start to work on the enthalpy. So bond energy occurs when things bond and when they break up, okay? Basically, there's no kinetic energy involved. We'll learn about this in Unit 6 when we do gases, but for now, there's not a kinetic energy involved when bonds are broken, but instead, we think about potential energy. It's the potential energy that changes when a bond reacts, okay, or breaks or forms. Excuse me. So we call that the energy of the position in general, but we're looking at what's happening to the electrons in a bond. When you break a bond, there's potential energy stored in that bond where the electrons are, and those electrons and the breakage will release, will absorb energy, okay, in order to break that bond. When you form the bond, the electrons are going to be confined and they're going to have to release energy as they're forming. So this is just a little picture, okay, to remind you of how bonds are formed a little bit. Here's electrons, okay, and the electrons are repelled by each other. Okay, they don't want to get too close together. They've got to be far apart because of their negative charges. Likewise, our nucleuses with the positive charge also repel each other. Okay, so we've got repulsive forces happening, but at the same time, the electron and the nucleus are attracted to each other. Okay, and so at some position, they're just the right position, they're going to form a bond. So this is a little picture of a hydrogen bond. Okay, now let's start on this side. I'd rather start on this side than on the other side. Now we're looking at two separate hydrogen atoms, and you'll notice that this is the amount of energy. Okay, this is energy on this side, and this is distance. We'll talk about that in a minute. These two hydrogen atoms are far apart. They're not attracted to each other. There's really not much energy going on right here. Okay, they're not really attracted or repelled. They might be more repelled than attracted. But as they begin to get closer and closer together, so our distance is getting smaller and smaller, they begin to have interactions, okay, so that there's more energy related here because there's both attractive and repulsive forces, okay, but no bond has formed yet, okay, they're close but not close enough. When they get to exactly the right amount of distance, where there's exactly the right forces so that they're attracted exactly right, then when the bond forms, energy is released. Okay. So, and that should make some sense. Each of those electrons is moving, moving, moving. It's got its own little amount of potential energy, and then when they come together, some of that potential energy is lost. And then let's start the other direction. Okay, so let's assume that we have something's happened to this H2 molecule, and somehow they're starting to, the nucleuses are starting to spread out a little bit. Okay, so they're beginning to feel a repulsion away from each other because of whatever has happened to it. And let's say it comes back together, nothing bad happens, okay? So, well, no, let's don't say that. Let's say it actually breaks. The H2 breaks into two H's. In that case, we'll have the same amount of energy, but this time that energy has to be absorbed to break that bond. And that should just sort of make some kind of intuitive sense, I hope. Now, these bond lengths, okay, the exact length between the nuclei, this is the distance between nuclei. Is measured in something called angstroms. An angstrom, which is 1 times 10 to the negative 10th meters. Okay, so that's measured in angstroms. These have been converted into picometers to make it a little easier for you to see. I just want you to notice that because we're going to use that in a minute when we talk about bond length a little bit more. All right, so there's some properties of covalent bond. This is all covalent, by the way. We'll talk about ionic some other time. We're talking about covalent, though. And so we want to think about the bond orders. Bond orders is the number of electron pairs that form a bond. It takes 2 electrons to form a bond. And so bond order depends on whether it's a double, a triple, or a single bond. When it's a single bond, the bond order is 1. When it's a double bond, shockingly enough, the bond order is 2. And I bet you wouldn't be surprised to find out if it's a triple bond, the bond order is 3. So you're not really going to see anything outside of a single, double, and triple bonds for the most part. The bond energy, okay, is the energy that we need to overcome the attraction, okay, between those 2 atoms. So how much energy does it take that needs to be absorbed in order for the bond to break? So the stronger the bond, though, the higher it is in energy. Okay, so weak bond energy is a weak bond, and strong bond energy is a strong bond. And then the bond length, we just looked at that a little bit, is the distance between the nuclei of the bonded atoms. So, come back to that. I want to look at this bond energy table. Okay, so this is in your book in chapter 9. For example, here's a carbon-carbon bond, single bond. It has a bond energy of 347, and that's kilojoules per mole for all of these. Here's a double bond, carbon-carbon double bond, and it has a higher bond energy, which shouldn't be very surprising. And then somewhere in here, oh, it doesn't show anymore. It's lost, got lost, but here's a triple bonded carbon-carbon, and it has a much higher energy at 839 kilojoules per mole. I also want to look at something about fluorine and chlorine. Where are you? Oh, here it is. And let's say bromine. Okay. Now, fluorine is a very small atom, as you'll learn later. Okay, so there's not very much distance. This one is the distance between the two nuclei. Okay, and that has a kind of a low bond energy. Okay, when you get to chlorine, okay, double bonded, Cl2, now you have a bigger atom. Each chlorine is a little bit bigger, and so the distance from the nucleus to the nucleus is longer than it would have been for the distance between the nucleus and the nucleus for the fluorine. Okay, so let's notice that the distance gets longer because the atoms are bigger, and also the energy gets higher. And then if we take bromine, let's say it's this big, there's our nuclei. The distance, of course, is going to get even bigger, so longer, and in this case, we have a little bit of decrease in that bond energy. And that's because that's so big that it doesn't take as much energy as it did, for example, with the chlorine to break the bond. And we'll look at this more in a different unit. All right, so I was just going to go back. The strength of the bond is dependent on the attraction between the electrons and the nuclei of each set of atoms. Bonding energy is required to overcome the attractive force. Okay, so we need to add energy, heat energy, to break the bond. So the bond has to absorb energy that's endothermic. All right, and so I guess I said that right here. When we form a bond, we're going to release some energy, and that's an exothermic bond. Okay, now that's important because you're going to have to fix your signs based on what you're breaking or forming. Because notice that in this table, every single value for your energy here is positive. There's no negative value in this bond table. And you're going to use this formula where the enthalpy of your reaction is going to still be equal to the sum of the bonding energies we just looked at. But this time, it's the only time you'll see in this class where we're going to talk about the reactants minus the products. Okay, so when we did enthalpy for delta H of formation tables, we did products minus reactants. When we did enthalpy about temperature, we did temperature final minus temperature initial. This one is the other way around. Okay, and you have to change the sign, okay, from when the product is formed. Okay, so you have to change the sign from this lovely value when your product is formed. So let's do a problem. Now, we've done this problem once before. Okay, we did this with the enthalpy formation. So we've got some dinitrogen pentoxide forming nitrogen dioxide and some oxygen. And now, using bond energies, we're going to calculate how much that will be. Now, you don't know how to draw these yet, but you will. So I'm going to draw this for you. So I have I have two of these, and that's going to form 4 nitrogen monoxide, dioxides that look like that, and oxygen is double bonded like so. Now, in order to do this, I want to take the reactants, okay, so I'm interested in my reactants minus my products first. So let's think about what gets broken here. I got to break everything. I'm not going to leave anything unbroken. So I have 2 double bonded NOs, but because I have 2 of those in my equation, I have 4 double bonded NOs. And then I have 1, 2, 3, 4 bonds of NO, so 4 NO single bonds that I need to break in my reactants. But because there's 2 of these, I actually have 8 of those NO bonds. And then on this side, I'm gonna form, let's see, this is break, this we're gonna break, and this we're gonna form. Now I'm gonna form NO bonds, double bonded, and since there's 4 of those, I'll have to have 4 NOs. I'm gonna break 4 NO single bonds, and then I have this oxygen, so I have 1 OO to form. So, you're going to look in your book and you're going to find that this one is, I think, 607. This is 201. This is obviously 607. Oh, and this is kilojoule per mole. This is still 201. And the oxygen is 498. Still in kilojoules per mole. Now, technically, you're supposed to break everything and put everything back together. So let's do it that way first. Okay, so I'm going to take the sum of bond energy for the reactants, that's times N, plus the sum of the bond energy for the products, and that will be equal to my enthalpy value. So, actually, I'm just going to skip that because the truth is, you're smart, that's why you're in chemistry. Look, you've got 4 NO bonds here and 4 NO bonds there, right? So can't we just cancel that before we even get started? We're going to break them and then we're going to reform them. I mean, it's true they rearrange into a different, but for value purposes, they don't change. Then we have 8 NOs and 4 NOs. Okay, so I'm going to get rid of this. And I'm going to say I have 4 nitrogen monoxides or NO bonds on this side, and still I'll have the 1 double bonded O. All right, so now reactants minus products. So I'm going to say I'm going to break. Break 4 NO bonds at 201 kilojoules per mole. And then, remember the formula is plus, okay, I'm gonna have to now release energy when this bond is formed for, in this case, basically, the only thing I have left over here is this oxygen molecule. So I've got to release it, so minus 498 kilojoules per mole times 1 mole of oxygen. And when you calculate this up, it works out to be 306 kilojoules. 306 kilojoules. But we have a problem. When we calculated this using the delta H of formation tables, that value came out to be 219 kilojoules. So what's the difference? Well, difference is bond energies are averages of all sorts of bonds, okay? Any bond that is a carbon-carbon bond, or any bond that is an NO, not specifically for these bonds like they are for delta H of formation. So we're kind of in the same range, but bond energy is more of an estimate. You'd use this when you don't really know what that bond energy might be, where you haven't been able to find it out. That way you can at least see if you've got an endothermic or an exothermic reaction. You can see roughly the range that it ought to be in, okay? So bond energies are useful, but if you've got information in your delta H of formation table or even from your calorimetry experiment, that's probably more accurate than your bond energy values. So that's the end of Unit 3. There's 4 ways to find enthalpy, so you need to be familiar with all of those ways.